Hello, everyone. Can you hear me?
Yes.
Hear you loud and clear.
Okay,
Good
thank you.
afternoon.
Welcome to the AFOMP Industrial Webinar on X-ray Imaging QA tools today. My name is Dr. Byung-Chul Cho, and I have the honor of serving as your moderator for this session. Before we begin, a couple of quick housekeeping items. As you know, this webinar is a CPD endorsed activity. So to receive your points, please complete the feedback form. I will share a Google form link in the chat box before the Q&A session. And also throughout the presentation, please use the chat box on this Zoom meeting to share any questions or comments you have. I'll collect them and post them to our speakers during the Q&A session at the end. Let me introduce today's speakers. It's my pleasure to introduce our two excellent speakers from the RTI Group, a global leader in X-ray QA solutions. Our speakers are Ms. Christina Armanio and Mr. Eric Wikstrom. Christina serves as the Area Sales and Application Manager for RTI Group APEC, based in Singapore. Eric is the Global Training Manager for the RTI Group, where he leads the RTI Academy in Sweden. Together, they will be sharing their expertise on the topic that is essential for all of us in the field of the diagnostic X-ray imaging. So, without any more ado, please welcome Christina and Eric.
And
Recording in progress.
Excellent. So, thank you very much for that introduction. I'll just share my video. This is me, Eric Wikström. I'm in Sweden at the moment. And thank you very much for hosting this meeting and giving us the opportunity to share some of the information about X-ray QA. Now, just to give a little bit of a background, I'll start, give a little bit of background on the RTI company. I will hand over to Christina to lay the foundation for today's topic, which is scatter and leakage measurements and advancements in that field. But just to give you a bit of a background for RTI, it is a global company. We have a head office in Sweden, west coast of Sweden, and like we heard before, the sales office in Singapore, where Christina is in charge. We also have an office in the US, and the east coast of US in New Jersey, sales office, and also a service office where we perform calibrations and repairs, etc. And there's also an Europe Limited, which is in London, sales office and regional sales office in the UK. And looking forward, where were we active? Well, we are active in the field of medical X-rays. So, and specifically in the diagnostic part of it. So the next slide will show you where we are and where the focus is. So it's mammo, dental surgery. Also in the therapy part of it, where we have mega electron volt energies, there is the imaging or the onboard imagers, or the planning stages. Sometimes it's called the planning stage, which is a KV component in the therapy side as well. So that's where our focus lies. We do have some applications also in industrial X-ray, like in food, to calibrate X-rays that are monitoring the food, for instance, pick and place machines and electronics industries, etc. But that's a side business. If it happens to fit, that's where we are. Today's topic is scatter and leakage, and of course we see also in luggage scanners, for instance, that's also an important field to be able to monitor and to watch out for leakage. We have a family of instruments, of course, for X-ray. From the more simple ones, which is a cobia with a built-in screen, to RTI Mako, which is the most recent probe or system that we have on the market, which is for higher-end applications for all modalities, including mammography and panoramic dental, etc. So the probes and meters that we have are grouped into families. Wherever you said we had a cobia. The cobia is a range with different applications. Piranha is an old workhorse that we've had with us for a long time, where we have different types for different applications, ranging from the white one there is dental, mammography, CT, multi, and RF. So depending on where the application lies, we have a configuration for that. To handle other applications or other measurements, there's a bunch of external probes to be able to measure CTDI, for instance, beam width, MA, MAS. We have chambers that help us measure DAP, dose area product, or CAP, etc. So to make the selection more complete. We also have a scatter probe, which we'll be focusing on today, to be able to measure scatter and leakage. So it's the leakage and the secondary radiation in an X-ray application. That's what we're focusing today. The most recent system that we had, like I said, is this RTI Mako, which will be the workhorse for us in the future. Has a range of probes for RF, mammography, dental, and then also for ion chamber usage, MAS applications, and a legacy to be able to utilize legacy probes from the previous systems like Piranha, for instance. Those are then completed with a software package called Ocean Next, which is not only a display, but it's also an efficiency tool to help users make their workflow, improve their workflow when it comes to X-ray QA and measurements. History is quite interesting. RTI was founded a little bit more than 40 years ago as the first company to provide a non-invasive X-ray meter called the DigiX onto the market. So that was the market saw that 23 or 43 years ago, rather, the DigiX. And before that, of course, to measure a KV, for instance, in an X-ray machine, you had to disconnect the high tension cables and fit them into a voltage divider, and then make a measurement, connect your oscilloscope or a voltmeter, and then put everything back. So that would take, in best case, like 30-45 minutes for one exposure. Being able then just to put the detector into the field and make one exposure and have all those data in there in 2 minutes was a vast improvement, of course. Now in the 43 years that we've been in business, of course, the world has moved on, and we have more newer generations of products like the Barracuda, which many of you may have heard, the red Piranha, Cobia we spoke about, which is a meter with a built-in display, black Piranha, which is an update of the red Piranha that has been with us for a long time. And then 2020 and 2021 and 2024, we've got the most recent developments there with a new platform, software platform, Ocean Next, the scatter probe, and then the RTI Mako. And we're not stopping there. We do have more things in the pipeline for us. You may wonder why we're calling strange names like Piranha. We have the Cobia. We have the Mako. and they're all fish. Well, the history is that started already 25 years ago with the introduction of a system called Barracuda, where we said that we need a name that is good, that sounds strong. So that was the Barracuda, and then we've kept it, and it's followed with the Piranha, Cobia, and now Mako, and of course they all swim in the ocean, which is the software name of the software package. So that's a little bit just to keep in mind. Global customers, of course, we're working closely with the larger manufacturers to ensure that our systems work as they should in those environments. So we have close relationships with GE, with Hologic, very close. I mean, their service engineers in the US are all using RTI tools, and that tells us at least that it's a good sign of quality. But of course, all others, we're working with Siemens, we're working with the Canon, Samsung, Carestream, yeah, all larger manufacturers in the world to ensure that we have a well-functioning system for X-ray QA and testing. So that was a little bit background of RTI, just to for those of you who don't know that. And with this, I'll hand over to Christina. She'll walk you through the foundations of today's topic. So Christina, take it away.
All right. Thank you very much, Eric, and thank you for the introduction, Dr. Cho. Good afternoon to everyone who are joining us from Asia Pacific, and I think we may have other guests from other regions. So good morning, perhaps, to some of you. Good morning to Eric, who is in Sweden. So yeah, our key topic for this webinar is measuring leakage and scatter radiation in the context of diagnostic X-ray imaging environment. First, as Eric said, I am here to help lay the foundation for the topic today, and so we're going to do some terminology review. First off, radiation leakage. What do we mean by radiation leakage? Radiation leakage are all the radiation that passes through the protective tube housing, with the exception of the useful primary beam. And how about scatter now? Scatter radiation is different from the leakage radiation. Scatter radiation originates from the patient's body after the primary X-ray beam interacts with the substance. Now, a substance can either be the patient's body or the imaging table. And in a typical diagnostic imaging procedure, both types of straight radiation are present. So why is it important for us to measure the X-ray tube radiation leakage and scatter radiation? Both of these contribute to the unnecessary radiation dose to the patient and the staff. So as we said, these are not part of the primary beam, which is the useful beam. We call this stray radiation. And here we recall the concept of ALARA, or as low as reasonably achievable. And simply put, the ALARA is our guideline to avoiding exposure to radiation that does not have direct benefit to the patient as well as to the staff. Even if the dose is very small, we have to avoid it. So ALARA is basically our practical application of our understanding of radiobiological effects. And by adhering to the concepts of ALARA, we can prevent the deterministic effects, and most importantly, in this case, minimize the probability of stochastic effects, ensuring that the benefits of using radiation far outweigh the associated risks. Now, when do we measure leakage and scatter radiation? Let's take a closer look into this. The leakage and scatter radiation test occasions are usually done. I mean, for us, I am a medical physicist like you, for those who are joining us in this AFOMP webinar. Normally, what we know is we do the scatter and leakage measurements in the hospitals, X-ray installations. But usually this is also done during end-of-line testing when manufacturing X-ray tubes and X-ray machines. So in the factories, there are such things as tube leakage radiation testing as well. And of course, as I said, on-site installations during acceptance, performance, and conformance routine testing of this X-ray machines. Also, we would like to emphasize that scattering leakage radiation testing should also be done in security systems, such as those airport scanners that we see during security check at the airport. And another instance where we do scattering leakage testing is after the replacement of parts that may influence the dose output. So that's tube change, collimator change or repair, generator replacement or repair. Such tests, tube leakage and scatter measurements should be done during those occasions as well. All right, so there are standards for leakage evaluation, and two that we are very familiar with, and we have seen this being adopted all around the world. We do have first the IEC, of course, International Electrotechnical Commission, which says that 1 milligray in 1 hour is the limit. Measurement should be done at 1 meter from focal spot, and it should be measured over a 100 centimeter square area. This is very similar to the FDA requirements in the US. However, please take note that there's also additional standards when the tube is not discharging. And this is done at 5 centimeter from accessible surface, different from the 1 meter from source or the focal spot. And according to FDA, we do this at 100 centimeter square area. IEC says to use 10 centimeter square area. Now, at this point, I would like to please ask for your attention in 1 hour. So we have seen this a lot. We have been sharing about the standards of leakage whenever we do our visits to customers and other regulatories, medical physicists in the region. And we get the question, why not per hour? It is very important to remember the standards is saying in 1 hour, it is not equal to per hour. These are not similar things, very different things. So the standards say in 1 hour, not per hour, and this is to represent the maximum cumulative dose an area might receive from radiation that escapes from the tube housing, even when the tube is not actively producing an image. So this standard duration accounts for the total workload and ensures that the device is safe for staff and patient by limiting the total allowable leakage over a typical period, not just an instantaneous rate. So the values need to be normalized when we do the measurements for tube leakage. The values need to be normalized to what is plausible in 1 hour. So we do the workload calculation based on power rating and max KVP, set mass and typical mass consumption. And usually the settings is recommended by the manufacturer of the X-ray machine. However, if there's no recommendation from the manufacturer, you look into the requirements or the recommendations by your local regulatory body and use that when doing your tube leakage measurement and testing. All right, so now we mentioned again, going back to the topic, stray radiation is both not just tube leakage, but also scatter. So we said that during a normal exposure, both the tube leakage and the scatter can be generated. So this, of course, can be a concern from a radiation safety point of view, since this may impact adjacent areas around the X-ray room. And both the fluence and the quality of this stray radiation have an angular dependence. And it also does not have the same intensity in all directions. So it's a very special concern, especially in fluoroscopy procedures, which are longer. And to ensure the safe operation, radiation limits have been decided, and these are similar in many places around the world. So again, I think this is a review for many of you. Typically, the dose limits, that is not for the patients, but those limits we have for occupational, 20 millisievert per year, average over 5 years, and a maximum of 50 millisievert in any single year. And for public, we have 1 millisievert per year, average over 5 years, and maybe higher for any single year. So just to give us a comparison and put this in a context, for example, a one set of dental x-ray is 5 to 10 microsievert. Occupational limit, 20 millisievert, public 1 millisievert. So take note of the units. And here, we are using the unit of sievert. And why the unit of sievert came about is this is a tool to assess the risk to a radiation exposure. And the sievert is used as for radiation quantities such as equivalent dose and effective dose. And the sievert provides a single comparable unit to quantify the potential health risk of different types of radiation, also accounting to the different biological effects. So this is an SI unit. We know sometimes in the US they still use non-SI units, but I think in Southeast Asia or in Asia Pacific we are harmonized with the US SIs. And Sieverts is the SI unit specifically designed to represent the stochastic health risk of ionizing radiation, which includes the probability of developing radiation-induced cancer and genetic damage. And now when we do our scatter measurements, we use H star 10, which is also, of course, measured in sieverts. And this is used for the area monitoring of penetrating radiation. And the calibration is done to a dose to a point 10 millimeter under the surface of a reference sphere. And this is an energy dependence, and this is higher energies because higher energies can penetrate more. So since we're talking about risk evaluation, to reduce the risk, I believe many of us are aware or perhaps already have been involved in doing shielding calculations. So in the X-ray room, we typically use a lead line, or we do solid concretes, and this is done during the design phase and the calculations are based on the equivalent lead thickness standard of lead glass. So usually, during the shielding calculation, there's already a safe margin, and making sure that the stray radiation does not penetrate through the shielding. However, still, risk assessment should come in because there could be issues that later on there is a chance that I don't want to say this, but perhaps we don't know if the contractors didn't do a good job or didn't use the required thickness that was designed during the shielding calculations. So this is where the occupational safety hazard assessments or safety checks need to be done. And whenever we do this shielding surveys, we do use the word survey because we do go around the X-ray room. We do factor in factor of time that this adjacent rooms around the X-ray room are occupied. And here we go use what we call the occupancy factor. And usually the use of the occupancy factor when doing our shielding calculations leads to a normalized dose. And this indicates the amount of time that these areas where that is adjacent to the X-ray room are actually occupied. So normally there are very little changes to this, but as I said again, there could be instances over a period of time that some issues arise, and so we do our measurement and testing for stray radiation. And so at this point, I'm going to give you back, after giving you the foundation of our topic today, how do we measure leakage? How do we measure scatter? And I'll pass you on to Eric. I will be stopping the presentation from my end, and Eric, please take over.
Well, thank you very much, Christina. I will see if I can share my screen. I found it there. So is my screen visible at the moment?
Yes.
Okie doke. Okay. Good. All right. So now we know why leakage is important, what we're looking for. I'd like then to just share a little bit about how to achieve the measurements, how to get about them. And when we're looking at leakage measurements, what we said is, like we said, it's the radiation escaping the tube during exposure. And how do you do that? Well, first of all, we need to close the collimator during the operation, during these testing, so that we don't get any scatter splashing about and radiation scattering around when we're doing the measurement. So the collimator needs to be completely closed. Then setting the exposure techniques to maximum kV and maximum mass, or what is recommended by the manufacturer. And then measuring in 5 directions: in the front, the anode side, the cathode side, rear, and the top. And sometimes that is a bit of a challenge. Could be an issue with space, finding enough space to the side to position the meter. Here's our probe, the scatter probe, whichever probe you're using, positioning at 1 meter from the focal spot. That's what we need to try to achieve. Measuring from the top may be a bit tricky, but in many cases you can swivel the tube so that you can then, in that way, measure the leakage out of the top of the X-ray tube. Then when looking at scatter, that's a little bit of a different occupation. Like Christina was saying, is actually then the scatter generated by the secondary, so it's a secondary radiation. So it's generated by X-rays, a primary beam hitting a subject, and from there we get scatter, and it scatters in different directions. And so we need to generate scatter in a standardized way when we're doing this testing. So in most cases, what we do is we set up a stack of 20 centimeters high, a stack of PMMA slabs or other suitable phantoms for this, but this is a standard way of doing it. You open the collimator then to fully irradiate the stack of PMMA, and again set the technique to maximum kV or maximum mass, and then we may place the probe according to the measurements that we want to achieve. And that could be looking at the integrity of the lead glass into the control room. Is that actually the attenuation of the lead glass, is that proper? So then we can then, during the exposure, we can then have the scatter probe on the inside to see what kind of radiation penetrates the lead glass. Could be checking the door jams as well, to seeing here's a door. It might be a little bit tricky to see, but a door into the room, so you can place the probe, the scatter probe, right there. Here's a tube. Scatter is generated from the slabs and then shoots out in the different directions there, so we can see how efficient is the radiation trap in the door jamb. And inside the room, of course, we can then make a map, a dose map, to see what does it look like? Where do we have radiation, and how is that propagated in the room? So we can make like a heat map to see what does it look like in the room? Do we take the proper precautions when working interventional systems, for instance? So then you need to be inside, or the probe needs to be inside the room. And for those occasions, it's pretty good to have the possibility of placing it on a tripod. So you don't need to be able to, so you don't need to stand in the room and expose yourself to radiation. So those is the basics of leakage and scatter measurements. Sound pretty straightforward, but when we start digging into it, there are some challenges in there when it comes to measurement. And it is for that reason that we've developed a scatter probe for this. Now, what is it? Well, many of the traditional meters used for scatter and leakage measurements are designed for radioactive isotopes, for surveying larger areas to look for radioactive waste, for instance. They're not ideally suited then for the diagnostic imaging energy range, which is a mean energy of 10 to about 150 keV. That's where we have the spectrum that's interesting for diagnostic imaging. So they would need energy compensation for that energy range, at least or specifically for the energies below 50 keV. Which is the mean energy generated by a typical 100 kV setting on an X-ray machine. And of course, that's the mean energy, not the acceleration voltage, it's the mean energy of the spectrum. And you can, if you know, you can estimate the KeV, the mean energy, but it is challenging to do that and in a reliable way to get a proper energy compensation. So there are some risks in there. Like we said, it was the traditional usage there is to detect radioactive contamination of different sorts. So that's a continuous radiation, a long time radiation. So that's also then different from normal diagnostic imaging. So it gives them a long response time, the survey meters, typically much more than 2 seconds to establish a step in the output, which is what we have in a diagnostic imaging and an X-ray system. There are short events, so it's difficult for that kind of system to capture fast events like an exposure peak. So then long exposure times may be needed for it to do some sort of work, but then for that you need then to turn down the MA, the tube current, so that you reduce the workload on the X-ray machine. But that produces a weak output, a low dose rate, and that puts an extra challenge onto the instrument for sensitivity. And we know that that's also another challenging area for traditional meters. And if we need to crank it up for a long period of time, for longer exposures, that increases the wear on the tube. And then we've got mechanical design. Typically, there would be ion chambers used there, but they need temperature and pressure compensation in addition to the energy compensation to give a proper value. If it's a pressurized ion chamber, of course, then it's also hazardous cargo. So that puts challenges on when it comes to shipping back and forth to sites and also to calibration laboratories. And they also then handheld, designed for handheld usage, which may be undesirable. If we don't know the radiation, we may want to place it there to be able to make a reading without being present in the room and being subject to radiation. So these are the main challenges that we see in the market. And what do they mean then? What are we talking about? Just to give you a better idea again, energy dependence. So this is just typical curves of energy dependence that we see from in the market and other meters. And there are different scales here also. Here's a linear scale, produces this curve. And then you may see also logarithmic curves that look like this. So here you see that it's this is one where the reading is proper, and it happens only up here, which is around 800 keV, and down here, which is 20, 30, 40, 50 keV, which is up here. That's when it shows the right value. For other values, we need to compensate. And then we need to know the energy range, and pretty precise, because this is a very steep curve. So even the slightest change or difference takes us from here, which is 10% off, to down here, which is 60% off, just if we're 10 keV off in our estimation. So that's a little bit of a challenge. If we look at the logarithmic scale here, also it shows you in even more clearly what we're talking about. So this is then quite a big part of the diagnostic imaging energy range that we're talking about, where we need to compensate. All right. So what is a practical impact then? Okay, let's just remember here that what the curves look like a little bit. If we take an example of different exposures, say that we make an exposure here of 50 keV, we set the for 100 keV on the console. That gives us a mean energy of 50 keV for the spectrum. And this would be the output that we're seeing from the tube. Just imagine that we are. But so if we're at 50 keV, this is at that point, we'll see it traces the reading pretty well. It will rise slower because, of course, it has a longer response time to reach that value. And if there is some bumps in the road or some peaks or some other, it will also react, but slowly to that phenomenon. But it will give us a max reading, which is true, which is the same as the actual tube output. Well, what happens if we have set the X-ray machine to 35 keV set value? That gives us a spectrum of about 26 keV. So we have that. This is the actual output, tube output, but it will underestimate the output quite a lot because of the energy dependence. If we have set it for 160 keV for some reason, we have a 60 keV or 70 keV, for that it will overestimate the leakage or the radiation. And if we look at mammography, which has been said that, oh, we don't need to worry about mammography, we don't see anything, maybe that is because it underestimates the leakage in here. So that's maybe a reason why maybe there is, the radiation is so weak that there is no risk involved, but then again we don't know. We need to be these are the risks that we're running with traditional meters that we're there. So that's when it comes to leakage, when we're looking at the air kerma for it from an X-ray machine. Now there is also some difficulty to measure or to assess this ambient dose equivalent, the H*10 in Sievert. So there's some people that say that, well, it's more or less the same. So we're just looking at the air karma. Well, it is different because we're assessing the dose to a point 10 millimeters into the skin. So there's a radical difference there. So, but if you do make the mistake of assuming that the ambient dose equivalent, the H star 10, is equal to the air karma, well, you'll be correct in one point of the curve, which is at 29 keV approximately. That's where air karma and ambient dose equivalent are the same. But for all others, there's a big difference. If we're looking at energies below 29 keV, well, it will overestimate the ambient dose equivalent. So you're wrong there. And if the energies are above, we're then looking at an underestimation of the ambient dose equivalent. So we need to know what we're doing when we're trying these what do you call it, exchanges or equations. Right, so that's the energy dependence. So there's challenges there. We talked about response time, and what do we mean by response time? Well, response time is if we have a curve like this with illustrating how an instrument responds to a step change in radiation. So you apply something, and this is how it then reacts. At 90, when it reaches 95% of maximum, that's what is defined as the response time. Now, if we apply or we make an exposure, an ideal exposure, say, like a square wave or rectangular wave, this would then be the exposure time. So we have an immediate rise, and that's when the instrument starts reacting. But here we have a response time which is longer than the exposure time. How does that affect the whole measurement? Well, the reading will, of course, grow according to the response time curve. But when the exposure stops, it will then discharge, it will then reduce. There's no energy there or no radiation to make the reading rise. So it will then just taper off. It will go back to zero. And that gives us an underestimation of peak dose rate when we're there. So the instrument will, after the exposure, will give you this reading as the peak dose rate of this exposure. So it's an underestimation of the peak dose rate when we're looking at it. And like we said before, the response time is typically 2 seconds or more. So we're looking at a new approach. We designed took the experience that we had and designed a scatter probe where we have a much better energy dependence. So this is the what do you call it, the energy response of the RTI scatter probe. For both air karma and for ambient dose equivalent, we're well within the plus minus 10%. Here is 1, here is 1.1, 0.9. So we're well within plus minus 10% for both of those in the complete range. And how is that achieved then? Well, the sensor surface is a matrix of solid state detectors, and we use a step wedge principle similar to what we have in our instruments for QA to assess that. And that gives us the possibility with the step wedges there and filtering and comparing ratios between these sensors to determine not only the dose or the air karma, but also the HVL and the mean energy, the KEV. And with the algorithms that we have, we can then estimate the ambient dose equivalent also with a high accuracy and reliability. And being solid state, it's quicker and it has a higher sensitivity than we see in, at least in ion chamber-based systems. So with this, if we compare, this is what we have in the market today. We can offer this in this performance across the full diagnostic and interventional energy range. And what does that bring then? Well, we saw these curves first, and if it's the same here, we'll see you see to have a better response time, so we've tracked it easier. Even if there is a bump in the road, we can monitor that, and we come up to the right value. Same thing here. It matches all along the waveform for all energies in the diagnostic imaging range. And looking at the response time as well. We see here that this is the display that we have for the RTI scatter probe. And this is a reading that we're doing from a leakage. It turns out that it's 28 nanogray, so you see it's quite low. But look at the response time that we have here. From the start, the triggering, and this is a self-trigger, the automatic trigger, the built-in. From here, it's less than half a second until we're up into the maximum of the output. The maximum, not only 95, but the maximum. If we look at the lower dose rate, a weaker signal, here we're playing with something that is 30 microgray, and the total dosage of 4 nanogray, which is very, very little. Again, we see from the background radiation, when it starts here, we're at about 0.6 seconds here until we reach 95%. And if we have an even smaller one, when we're looking at it, this is what we're seeing: 3 nanogray, also then 13. And here, it was difficult to see in this image here, but looking at it from here to there, I mean, the complete exposure, that's about 1.2 seconds. And then if we divide that by 2, again, the response there is 0.6 seconds. So that's a lot quicker. And also for radiation with very, very low dose rates that we've got here. So, and this is what it looks like when we have it on a close-up. We've got a 10 square centimeter area for some of the steady state applications, and we have 100 square centimeter area right here for most of the leakage, for the leakage radiation, and also for scatter radiation. So there's both compliant, both according to IEC and to FDA. Since we have the built-in, since we also assess or we measure the KEV, we have a built-in energy response. So there's no need to go into any manuals or tables to look at the compensation tables. It's the value you get is already compensated. So, and it's then in RF, DEXA, being bone densitometry machines, mammo, dental, and CT. It covers the full range of those applications there. So it's used by manufacturers globally to test, both in the production units and for field service. So it's, like I said, solid state, has a high sensitivity and good accuracy, and it's compatible with the Ocean software. And you saw the display there on which is the simple one. There is also the possibility of using templates in the Ocean. So here's one example of a template set up to measure the leakage from a tube in 5 different areas: front, anode, rear, cathode, and top. So we feed it with the settings that we've made. Maximum continuous MA, that gives us how many exposures like this can be done in 1 hour. We position it here, so wherever we can, let it know that the reference distance is 100 centimeters, that's 1 meter. So if we can place it at 1 meter, that will be fine. Then we'll be positioning it here. And then we just make exposures. The data is collected and populated directly from the scatter probe into the template. And the readings are made. And recalculations are made in here automatically based on the inverse square law. So here you see that we're positioning at 2 meters, but we get a fail here. And why is that? Well, probably because that was position was not at 2 meters, it was actually at 75 centimeters. So if we enter that value, and after we made use the tape measure, you can see that, okay, then the calculations are redone and we get a pass and everything is fine. Once that is done, you can also produce a report with all the data for each position and serial number of the scatter probe for traceability. So just to summarize then again what we've spoken about here, that scatter and leakage is quite important. It's necessary to be done. It's required by many regulatory bodies. But we need to keep that in mind, that energy dependence has a big impact on traditional leakage and scatter measurements or instruments. They have a long response time, typically 2 seconds or more, even if the radiation, if the dose rates, if the radiation is weak and the dose rates are low. And many times they're designed to be operated by hand. So that's those are the challenges that we see. So what we offer here then, and what we've talked about today, is the scatter probe with energy dependence built in, or the compensation for the energy dependence is built in to the firmware. With fast response of solid state detectors mountable on a tripod or handheld possibilities. So you have, when you're doing survey looking for leakage or weak leakage spots around a tube or in the door or wherever. So you have those 2 options. And connected to a software where you can save and print the measurement data for review later on and comparison later on. So this is the presentation that we had, and thank you very much for your attention. This is the emails for us. If there is any questions that you have that you'd like to direct to us in person, that's fine. You can post the questions here in this chat as well. And if you would like some more information, here is a QR code that would direct you to some more information on about the scatter probe. So with this, we are open to any questions that you may have.
Thank you, Eric and Christina, for your excellent talks. And I'm looking at the chat box, but actually there is no question. Only one question, but it is already answered by your talk. So that the RTI scatter probe is based on solid state, right? It's not a
Yes, sir.
ion chamber.
Yes.
And I guess it is a great breakthrough to flatten the energy dependency over all range of the diagnostic X-ray. So congratulations.
Thank you very much.
Yeah.
Yeah. No, it's, and what we're seeing also is that we initially we've had it and we have customers using it now for since 2021. And sometimes there is a bit of a challenge to when we're being compared against older systems or other systems which may not have the same sensitivity. So, but now we're seeing that it's getting more and more accepted. So I think we're happy to be able to help to provide tools to make sure in a better way, is there radiation or not, and to what extent is there radiation. So at least that we know, that we don't ignore anything, but so that we base our decisions on knowledge instead of tradition. That's what we'd like to do.
Thank you. There is one question. Christina, you explained about in 1 hour and per hour is different concept. So there is a question about that. Yeah.
Yeah, so we would like to emphasize when we're doing the calculations for for leakage, what we account for is not in 1 hour, sorry, not per hour, but in 1 hour, because in 1 hour, it represents the maximum cumulative dose that an area might receive from radiation that escapes the tube housing, even when the tube is not actively producing an image. And it also accounts for the total workload of the machine. So if we just say per hour, it's instantaneous measurement of the dose as compared to per hour. Yeah, and that's why usually when we do the calculations, what we have is we account for like how many hours a staff might be working, for example, inside the room or in the control console room, and then we account for the workload. Is the staff working for 8 hours or only maybe 6 hours? Yeah.
Okay, there is another quick question. Are there sensors applicable to dental X-ray and mammo, or different instruments should be used?
Sorry, could you please repeat that, Dr. Cho?
Oh, yeah. You can find in chat box by
Yeah.
yourself.
Let me see. Uh-huh.
I think your the scatter probe can be also applicable to dental X-ray, right? And
Yes,
also
definitely. Yes.
yeah.
So any medical X-ray machines, even bone densitometer or DEXA, dental, mammo, CT, radiofluoroscopy, GenRad, as some people call it, or general radiography, fluoroscopy, interventional angiography machines, uh, you name it all. As long as there's an X-ray machine at the heart, X-ray tube at the heart of that X-ray machine, we can use the scatter probe to do the scatter and tube leakage measurements. Yeah. And the good thing is that being a solid state detector, the RTI scatter probe is really, really sensitive, so it can measure very low dose of radiation.
So yeah. I
Yeah.
personally I had many years ago, I tried to measure the exposure from the CT. I'm working on the radiation oncology department. We have a simulation CT.
Oh, yeah.
So trying to using the ion chamber what we are using, and try to measure the the leakage or scatter from the CT. But I was also suspicious about my results, because, as you say, it suffer from some delay time, right? Response delay, and also it is difficult. Even I calibrated the ion chamber using a certain the X-ray spectrum, but it is not close to my own CT. So how can I believe that result? So that was big trouble.
Thank you for sharing your experience, Dr. Cho.
Yes.
Yeah. So I was just looking also at some of the questions again in the chat, and there's a question of how can we use the scatter probe for measuring the background radiation? So Eric, would you like to take that? Because the scatter probe actually normalizes to the background radiation. Yeah.
Yeah. No, so when we make a connection and at the start of every measurement sequence or measurement session, the scatter probe is reset to the background radiation, and so that's where the zero level is. Now, of course, we can wait until the cows come home for it to trigger when we're using the built-in trigger. But there is a manual trigger function which is called free run mode, and which then starts the measurement immediately by pressing a button. And from there, you will then be able to follow and see if there are changes to the background radiation. And to get the absolute value, well, that's a little bit difficult. And since it's not a survey instrument as such, it is then the purpose of it is to monitor and see the additional radiation, what's produced in addition to the background radiation. So that's why it's if we don't measure the absolute value, then it's a value from referenced from the background radiation. But we have seen that it actually does capture changes in background radiation. Sometimes it also will show, after a long period of time, it may even show a negative value if the background radiation drops a little bit. That is the level of sensitivity that we have in the scatter probe. But that doesn't occur very often. So I hope that is a response. Sets it back, resets it to the background radiation, and looks at the radiation that is added due to man-made radiation like X-rays.
Thank you, Eric. We are almost running a bit out of time. We probably can capture 3 more questions, if that's okay, Dr. Cho, that we see here in the chat. And then what do you think?
Sure. That's fine.
Yeah. Okay. So I'm just Eric, I'll scan through this and please help me here. We have a question about how to compensate in measuring the scatter from a detector with an area of less than 5 centimeters square. This is quite vague, and I would request Mr. Rahoman Reddy to please send us an email just to clarify that, because I am not sure if he would like to ask that if the measurement area is less than 5 centimeter square, or is it the detector that is 5 centimeters square? So I think it's best to clarify that question before we answer it. Area survey through RTI scatter probe. Points of care.
It's also, I mean, an area survey would be okay if we have and that would be looking at door jams, looking at the throughput through a wall and stuff like that, and that's fine. It has the sensitivity for it, so would be one part of work that could be done. Points of care, well, I don't really know what the questioner was meant by that. Point of care, if that's has to do with what we need to watch out for, well, we recommend calibration every 2 years, and normal care for an instrument. Don't drop it, and be a little bit careful with it, and that's about it. So it's a comparatively robust instrument for that.
Thanks, Eric. And I think we'll take the last one, Dr. Cho. I know our time's up, but the very last one. This is from India. Why the measurement data shows repeatedly in scatter probe, like 0.1232 milliröntgen per hour, and at times 0.2054 milliröntgen per hour. And when we are shifting the scatter probe, we are skeptical that this changes in the display are actually real measurements or just standard being data being displayed by the probe.
Yeah, and again, these are very low values, of course. So it's difficult to know if they're relevant. And it could also be if it's shifting around. It may be that we're jogging the, what do you call it, the probes a bit, so disturbing it mechanically. Difficult to know. We need some more information about that, but the values here indicate very, very low radiation. So it's I would think that it's difficult to say what the reason is. Like we said, we need to be a little bit careful. We can't bang it around. We need to be careful when we're moving it. We have similar experiences if you're looking at ion chambers. They also self-trigger and jump around when it's being moved. So we need to keep that into account as well when we're there.
Thank you so much, Eric. And thank you so much, Dr. Cho, for letting us accommodate the questions. We know we're out of time now, so we pass back the ball to you, please. Yes.
Okay. Thank you everyone to join this webinar, and thank you for the nice talk, Eric and Christina also. And please keep in mind to complete the feedback link, complete the feedback form to get the CPD points before you leave. And thank you very much. We are close this session. Have the great weekend.
Thank you very much.
Thank you very much, Dr. Cho, and thank you very much to everyone who joined us on a Sunday. We look forward to collaborating more again with AFOMP in the future. Have a good weekend, everyone, and until next time.
Bye.
Bye.
Recording stopped.